Good evening, ladies and gentlemen. Welcome to another journey through the quiet wonders of the universe. Tonight, as you settle in, close your eyes, and let your mind drift into calmness. We will explore one of the greatest mysteries in modern science: dark energy. It's invisible and touchable, and yet it makes up most of our universe. For centuries, people looked up at the night sky and believed the stars were fixed, eternal, and unchanging. But today, we know the cosmos is alive, constantly expanding, driven by a mysterious force that scientists call dark energy. So, relax, let your thoughts float as freely as the galaxies, and let us explore what makes the universe expand. When we look up at the night sky, it feels eternal and unchanging. The stars twinkle quietly, the moon rises and sets, and the constellations appear fixed in place, just as they were for our ancestors thousands of years ago. For much of human history, the sense of permanence gave us the idea that the universe itself must be stable, constant, and forever the same. The heavens were considered the backdrop against which the drama of life played out, not a participant in the drama itself. Even the greatest minds of the past, philosophers and early scientists, could not imagine that the universe as a whole was moving, stretching, and transforming on a scale beyond comprehension. At the beginning of the 20th century, a brilliant thinker named Albert Einstein entered the stage of science. His work revolutionized the way we understood space, time, and gravity. In 1915, Einstein introduced the world to his theory of general relativity, a framework that showed how matter and energy bend the fabric of space and time. This theory explained how planets orbit stars, how light bends around massive bodies, and how the cosmos itself should behave under the influence of gravity. Yet even Einstein, with all his boldness, was reluctant to accept that the universe could be anything but static. His equations suggested that gravity, the universal pull that attracts matter together, would eventually cause the universe to collapse in on itself. To prevent this fate, Einstein added a mysterious term to his equations, something he called the cosmological constant. This was a kind of mathematical patch, designed to balance the attractive force of gravity and keep the universe motionless. For a time, Einstein's static universe was comforting, elegant, and in harmony with the centuries-old belief that the cosmos was eternal and unchanging. But not long after, evidence began to emerge that would challenge this picture in ways even Einstein could not have foreseen. Across the Atlantic Ocean, in the United States, a quiet revolution was taking place in the Arizona desert and on the mountaintops of California. At the Mount Wilson Observatory in Los Angeles, one of the most powerful telescopes of its time was being used by a man who would forever change our understanding of the cosmos: Edwin Hubble. Hubble was a curious figure, a lawyer by training, a soldier in World War I, and later an astronomer with a passion for exploring the heavens. In the 1920s, he began to study what astronomers then called nebulae, faint, cloud-like patches of light scattered across the sky. Many scientists believe these were small clouds of gas within our own Milky Way galaxy. But Hubble noticed something remarkable. By measuring the brightness of certain variable stars within these nebulae, he discovered that they were far too distant to belong to the Milky Way. These were not clouds of gas, but entire galaxies, vast islands of stars, each one containing billions of suns. The universe, it seemed, was far larger than anyone had ever imagined. But the most astonishing discovery was still to come. Hubble, working with his colleague Milton Humason, measured the light from these distant galaxies with great care. They found that the light appeared shifted toward the red end of the spectrum, a phenomenon known as redshift. This effect, explained by the Doppler principle, indicated that the galaxies were moving away from us. The farther away a galaxy was, the faster it seemed to be receding. This was not just motion through space, like cars driving down a highway, but the stretching of space itself. The universe, Hubble realized, was expanding. The implications were profound. The cosmos was not static at all. It was dynamic, growing larger with time, as though the fabric of space were an elastic sheet being stretched in every direction. What had once been thought of as eternal and unchanging was now seen as evolving, restless, and alive with motion. When Einstein heard about Hubble's findings, he was said to have visited the observatory himself and looked through the telescope. The evidence was undeniable. The universe was expanding. Einstein later admitted that his cosmological constant, the mathematical trick he had added to preserve a static universe, was his biggest blunder. Ironically, however, that very constant would return decades later as one of the leading explanations for dark energy. The discovery of the expanding universe changed not only science, but also philosophy and culture. If the universe was expanding now, it must have been smaller in the past. This realization led scientists to the idea of the Big Bang, a moment when the universe itself began in an unimaginably hot and dense state, expanding outward over billions of years to become the cosmos we see today. Suddenly, questions about origins, time, and destiny took on new meaning. The universe was not infinite and unchanging, but rather had a history, a beginning, and possibly even an end. Hubble's observations gave rise to what is now known as Hubble's law. The farther away a galaxy is, the faster it recedes from us. This simple yet powerful relationship became one of the cornerstones of cosmology. It suggested that space itself was stretching, carrying galaxies along like raisins in a rising loaf of bread. The bread expands, and the raisins move apart, not because they are traveling through the dough, but because the dough itself is swelling. In much the same way, galaxies are not racing through space, but are being carried apart by the expansion of space itself. As you let these ideas wash over you, imagine yourself floating far out in the cosmos, beyond the reach of Earth, beyond even the spiral arms of the Milky Way. From this vantage point, you gaze into the depths of space, and everywhere you look, galaxies drift away, their light stretched into longer and redder wavelengths by the cosmic expansion. The silence of space surrounds you, vast and endless. As the universe itself breathes and grows, the story of the expanding universe is not just a scientific tale, but also a deeply human one. It shows how curiosity, careful observation, and imagination can overturn centuries of belief. It reveals that reality is often stranger and more magnificent than we first suppose. From Einstein's equations to Hubble's telescope, we learn that the universe is not a quiet stage upon which life and history unfold, but an active, dynamic presence that continues to evolve on scales that span billions of years. Tonight, as you rest and listen, allow your mind to wander across that vastness. Picture the galaxies, each one a city of stars, drifting apart in a grand cosmic dance. The universe is expanding, and we are passengers in its unfolding story. From the thoughts of Einstein to the eyes of Hubble, from the equations scribbled in notebooks to the faint light gathered by telescopes, this chapter in the tale of dark energy begins with the profound realization that the cosmos is far from static, far from still. It is alive with motion, forever stretching into the unknown, carrying us along with it in its endless expansion. When we speak of the universe expanding, the natural question follows: what is driving this expansion? What force or presence is pushing galaxies apart, stretching space itself, and accelerating the grand unfolding of the cosmos? The answer, or at least the placeholder name scientists have given to this profound mystery, is dark energy. The very phrase itself carries an air of enigma. It suggests something unseen, something intangible, something that resists our ordinary methods of perception. Dark energy is not light, it is not matter, and it is not anything we can hold in our hands or even detect directly. Yet by all accounts, it dominates the universe, making up nearly 70% of its total content. Imagine that for a moment. Everything we can see, every star and planet, every galaxy and nebula, every atom of dust and gas, is only a small fraction of reality. The rest is hidden, a shadowy presence that reveals itself only by its effects. To understand dark energy, it helps to remember how expansion works. When Edwin Hubble discovered that galaxies are moving away from us, the assumption for decades was that the expansion must gradually be slowing down. After all, gravity is always attractive, the combined pull of all the matter in the universe. from the smallest particles to the largest galaxy clusters, should work against expansion, gradually decelerating it over time. If you throw a ball into the air, gravity slows it until it stops and falls back. By analogy, scientists thought that while the universe was expanding, gravity would act like a cosmic brake, pulling everything inward, maybe even reversing the motion one day. But at the end of the 20th century, astronomers were stunned to discover that this was not the case at all. In the 1990s, two independent teams of scientists set out to measure how quickly the universe's expansion was slowing. They observed distant Type Ia supernova, exploding stars that act like cosmic beacons, their brightness so consistent that they serve as reliable yardsticks for measuring distances across space. By comparing how bright these explosions appeared with how much their light was redshifted, the teams could estimate both how far away the galaxies were and how fast they were receding. What they found turned expectations upside down. Instead of slowing down, the expansion of the universe was speeding up. The galaxies were not only drifting apart, but accelerating away from each other, as if some invisible force were pushing them outward. This discovery earned the Nobel Prize in Physics in 2011, and it remains one of the most astonishing revelations in modern science. This is where the name, dark energy, comes in. Scientists needed a term to describe whatever was driving this acceleration, even though they had no direct evidence of its nature. Dark does not mean evil or sinister, but rather unknown. It is dark in the sense that it eludes our instruments, unseen and mysterious. Energy refers to the fact that it seems to behave like a property of space itself, a pressure or force embedded in the fabric of the cosmos. Unlike matter, which clumps together under gravity, or radiation, which weakens as it spreads, dark energy appears to remain constant or even grow stronger as space expands. It does not dilute as galaxies drift apart. It continues to push with the same or even greater intensity, fueling the acceleration we observe. There are many ideas about what dark energy might be. One possibility is that it is the modern reincarnation of Einstein's cosmological constant, a built-in energy of empty space. In this picture, even the void is not truly empty. Space itself possesses energy, and this energy exerts a repulsive force, stretching the universe. Another possibility is that dark energy is something dynamic, not constant at all, but a field that changes with time, like a vast ocean whose currents shift and evolve as the universe ages. This concept is sometimes called quintessence, an echo of ancient philosophy where a fifth element, beyond earth, water, air, and fire, was thought to fill the heavens. Others propose that dark energy may not be a new substance at all, but rather a sign that our understanding of gravity is incomplete. Perhaps Einstein's theory, as brilliant as it is, needs refinement when applied on the largest scales. In that case, what we call dark energy could simply be the footprint of a deeper law of nature that has yet to be revealed. To grasp the strangeness of dark energy, imagine an infinite balloon. At first, you inflate it slowly, each breath adding a little more volume, the surface stretching outward. But then, without explanation, the balloon begins to expand faster and faster, as if some unseen hand is pulling at it from all directions. You do not see the hand, you do not know what it is made of, but you know it is there because of the effect it produces. That is the position scientists find themselves in with dark energy. They cannot touch it, but they can measure what it does to galaxies, to light, to the overall geometry of the universe. The most remarkable thing about dark energy is how overwhelming it is compared to everything else. Matter, both the visible kind that makes up stars and the invisible kind we call dark matter, together account for about 30% of the cosmos. Radiation, the relic light from the Big Bang, is negligible in comparison, but dark energy alone makes up the lion's share, about 70%. This means that the ultimate fate of the universe, its future trajectory, is determined not by the galaxies we see, but by the mysterious presence we cannot see. It is as though we are watching a grand performance, dazzled by the actors on stage, only to discover that the true director remains hidden in the shadows, guiding the entire production with unseen hands. For now, we know dark energy primarily through its consequences. We see its imprint in the way galaxies spread apart, in the faint afterglow of the cosmic microwave background, and in the large-scale structure of the universe. The web of galaxies, stretching like filaments across space, forms patterns that would not exist without dark energy's influence. On every scale we examine, its presence becomes unavoidable, like a ghostly current beneath the surface of an ocean, moving ships whether or not they feel the wind. And yet, despite all of this, our understanding of dark energy is still in its infancy. We give it a name, we measure its effects, but we cannot say with certainty what it is. Some scientists wonder if it is even a single thing at all, or if it is merely the label we use for a collection of mysteries not yet unraveled. In this way, dark energy is both humbling and inspiring. It reminds us that even in this age of technology, and telescopes that can see billions of years into the past, there are still questions bigger than our answers. It reminds us that the universe is not only vast in scale, but deep in mystery. As you listen, let your imagination drift into that mystery. Picture the universe as a boundless ocean, with galaxies as little boats carried along by waves they cannot control. Beneath the surface of this ocean lies dark energy, unseen but powerful, swelling and shifting, guiding the motion of all things. Every star, every planet, every atom, even you and I, are participants in this expansion, carried outward on the currents of a cosmic sea whose nature remains hidden. You do not need to grasp every detail or formula to appreciate the wonder of this. All you need is the image of galaxies drifting, space itself stretching, and an invisible presence that whispers through the cosmos, shaping the destiny of all things. When scientists speak of dark energy, they are not describing something they have directly seen. Unlike stars, which shine with brilliant light, or planets, which reflect the glow of their suns, dark energy is invisible. It cannot be captured in a photograph, weighed on a scale, or bottled in a container. And yet, despite this invisibility, the fingerprints of dark energy are spread across the cosmos. We know it exists not because we see it directly, but because we see what it does. Its effects are written into the light of distant galaxies, into the patterns of cosmic radiation, and into the large-scale architecture of the universe itself. It is like the wind. You cannot see the wind, but you see the leaves moving, the branches swaying, and the waves shifting on the surface of the sea. By its influence, its invisible push, you know it must be there. The first and most direct line of evidence for dark energy came from the study of supernova. In the 1990s, two groups of astronomers, working independently, decided to measure how quickly the universe was slowing down under the pull of gravity. The reasoning was straightforward. If the universe has been expanding since the Big Bang, then gravity, pulling inward, should gradually slow the expansion. By observing how much the expansion had slowed over billions of years, scientists hoped to learn more about the balance of matter and energy in the cosmos. For this purpose, they turned to Type E, a supernova, some of the most powerful explosions in the universe. A Type E supernova occurs when a white dwarf star in a binary system collects enough matter from its companion star to ignite a runaway nuclear reaction. The star detonates in a burst so luminous it can briefly outshine an entire galaxy. What makes these supernova especially valuable to astronomers is that they all explode with nearly the same intrinsic brightness. Because their true brightness is known, astronomers can compare it with how bright they appear to us, allowing them to calculate how far away they are. They are like cosmic mile markers scattered across the universe, reliable and bright enough to be seen billions of light years away. When the two research teams examined these distant supernova, they expected to find evidence of a slowing universe, but what they discovered was startling. The supernova were dimmer than predicted, meaning they were farther away than expected. This could only mean that the expansion of the universe had not slowed, it had sped up. The galaxies carrying these supernova were racing away faster and faster, as though some unseen force were propelling them outward. The discovery was so unexpected that scientists double-checked and triple-checked their data, but the conclusion remained. The universe's expansion was accelerating, and something was causing it. That something became known as dark energy, but supernova are not the only line of evidence. The afterglow of the Big Bang, known as the cosmic microwave background, offers another window into the presence of dark energy. This faint radiation, discovered in 1965 by Arno Penzias and Robert Wilson, is the cooled remnant of the universe's birth, stretched into microwaves by billions of years of cosmic expansion. Sensitive satellites like the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe WMUP, and the Planck spacecraft have mapped this radiation with extraordinary precision. The tiny fluctuations in the microwave background reveal how matter and energy were distributed in the early universe, and from these patterns, scientists can infer the geometry of space. If the universe contained only matter, its shape would be different than what we observe. But when astronomers compare their observations with theoretical models, they find that only by including dark energy can the data be explained. Without it, the universe would not look the way it does. Dark energy, in other words, leaves a signature not only in the present expansion, but also in the ancient light that has traveled to us from nearly the dawn of time. A third line of evidence comes from the large-scale structure of the universe, the distribution of galaxies and galaxy clusters across cosmic space. When we map galaxies, we do not find them scattered randomly, like grains of sand tossed onto a table. Instead, they form a vast cosmic web, with filaments of galaxies stretching across millions of light years, intersecting at dense clusters, and surrounding immense voids of almost empty space. This structure grew from tiny fluctuations in the early universe, amplified over billions of years by gravity. But the exact way in which these structures evolved depends on the balance of forces shaping the cosmos. Without dark energy, the growth of these structures would be different. The voids would not be as large, the filaments not as thin, the overall pattern not as we observe today. By comparing computer simulations with surveys of galaxies, surveys that chart millions of galaxies across the sky, scientists find again and again that dark energy is required to match the observations. Even the geometry of the universe provides evidence for dark energy. Imagine shining a flashlight across space. If the universe contained only matter and no dark energy, the paths of light would bend differently than they do in reality. By studying the angles of distant cosmic features, such as the apparent size of galaxies and the spacing of certain cosmic ripples called baryon acoustic oscillations, astronomers can determine whether space is flat, curved, or open. The results point toward a universe that is remarkably flat, but to achieve this flatness, a large portion of the universe's energy must be in the form of something other than matter. That something is, once again, dark energy. Taken individually, each line of evidence might leave room for doubt. Supernova could, in theory, be misunderstood. The cosmic microwave background could be interpreted in different ways. The distribution of galaxies could be influenced by other unknown factors. But taken together, the case becomes overwhelming. Like pieces of a puzzle that fit together to reveal a coherent image, these independent observations all point toward the same conclusion: the universe is expanding at an accelerating rate, and some unseen energy is driving it. It is worth pausing to reflect on how remarkable this is. For most of human history, our knowledge of the cosmos was limited to what could be seen with the naked eye. A few thousand stars, the arc of the Milky Way, the wandering planets, the phases of the moon. This was the extent of our universe. Even with the invention of telescopes, the universe expanded only slowly in our awareness. Then, in less than a century, we leapt from believing the universe was static and eternal to discovering it was expanding, and then to the realization that the expansion was accelerating. Each discovery pulled us deeper into mystery, each one unveiling a universe far stranger and more dynamic than we had imagined. Dark energy is not an abstract curiosity. It is the dominant factor in the universe's future. If it continues to act as it does now, the cosmos will expand faster and faster. Galaxies will drift so far apart that the night sky will eventually grow dark, and distant stars will vanish from view. The universe will become vast and cold, stretched beyond recognition. All of this flows from the faint signatures we detect in supernova, in the afterglow of the Big Bang, and in the web of galaxies across space. And so, when we ask how we know dark energy exists, the answer lies not in direct detection but in the harmony of evidence. We know it the way we know the presence of a hidden current in the ocean, the way we know the presence of wind in the rustle of leaves. We know it because without it, the universe would not look the way it does, would not behave the way it behaves, would not be the universe we live in at all. When Albert Einstein first introduced his theory of general relativity in 1915, it reshaped the way we understand gravity. No longer was gravity merely a force between masses, as Isaac Newton had described centuries before. Instead, Einstein revealed that mass and energy curve the fabric of space and time itself, and that objects follow the curves of this invisible geometry. Planets orbit stars not because of a mysterious pull, but because space itself is shaped by the presence of matter. The beauty and elegance of this theory transformed physics, and yet even Einstein himself could not escape the deep-rooted assumption that the universe was fixed and eternal. At that time, the idea of an expanding or contracting universe seemed strange, even absurd. For centuries, philosophers and scientists alike believed the cosmos to be static, a grand celestial stage that simply existed. When Einstein applied his equations of relativity to the universe as a whole, however, they did not yield a static picture. Instead, the mathematics suggested that the universe should be dynamic, either expanding outward or collapsing inward under the force of gravity. This was not what Einstein wanted to see. It conflicted with both his intuition and the prevailing wisdom of the day. To fix this problem, Einstein introduced a new term into his equations, one he called the cosmological constant. The cosmological constant was, in essence, a repulsive force, built into the fabric of space itself, designed to counteract gravity's attraction. It acted like a kind of cosmic pressure, pushing outward just enough to perfectly balance the inward pull of matter. With this addition, Einstein could have his static universe neither expanding nor contracting, but held in a delicate balance between two opposing forces. For Einstein, this adjustment was not a matter of deception or weakness, but of elegance. He believed nature must surely reflect harmony and stability, and the cosmological constant allowed his equations to preserve that vision. For several years, the static model satisfied both Einstein and the scientific community. But in the 1920s, Edwin Hubble's observations shattered the illusion. By studying the redshift of galaxies, Hubble discovered that the universe was not static at all, it was expanding. Galaxies were receding from each other, and space itself was stretching. This discovery made the cosmological constant seem unnecessary, even artificial. If the universe was expanding naturally, then there was no need to artificially balance the equations with an outward push. Upon realizing this, Einstein reportedly referred to the cosmological constant as the greatest blunder of his life. The story might have ended there, with the cosmological constant relegated to a historical footnote, a mathematical curiosity discarded once expansion was confirmed. But the universe had other plans. Decades later, in the 1990s, astronomers discovered that not only was the universe expanding, but the expansion was accelerating. Gravity alone could not explain this acceleration. Something was pushing galaxies apart more and more strongly over time. And suddenly, Einstein's abandoned cosmological constant seemed relevant again. In its modern interpretation, the cosmological constant is thought of as a kind of vacuum energy, an energy inherent to empty space. Even in the absence of matter, even in the darkest void, space itself is not truly empty. Quantum physics teaches us that the vacuum is alive with activity, with particles constantly flickering in and out of existence, a restless sea of energy bubbling beneath reality. If this vacuum energy exerts pressure, it could act as a repulsive force, stretching space just as Einstein's constant once did. In this sense, Einstein's so-called blunder may not have been a mistake at all, but a profound insight, decades ahead of its time. The cosmological constant is now one of the leading explanations for dark energy. When cosmologists describe the contents of the universe, they often use a model known as lambda CDM, where lambda refers to the cosmological constant and CDM to cold dark matter. In this framework, lambda represents the vacuum energy that drives the acceleration of cosmic expansion, while dark matter and ordinary matter shape the galaxies and structures within it. Together, this model has become the most widely accepted description of the cosmos, aligning with observations of supernova, the cosmic microwave background, and large-scale galaxy surveys. But there remains a tension, a puzzle that continues to trouble physicists. When quantum field theory attempts to calculate the amount of vacuum energy that should exist, the results are staggeringly larger than what we observe. The difference is not a small factor, but an almost incomprehensible mismatch up to 120 orders of magnitude. This discrepancy, known as the cosmological constant problem, is one of the greatest unsolved mysteries in physics. Why does the vacuum energy predicted by theory differ so vastly from the dark energy implied by observation? Why is the cosmological constant so small compared to what mathematics suggests, yet not zero? The balance seems almost too precise, as though the universe were tuned with extraordinary delicacy. For some, this tuning hints at deeper physics we do not yet understand. Perhaps our equations are incomplete, and a new theory will someday reconcile the mismatch. Others speculate about the multiverse, a vast collection of universes, each with different properties. In that view, only in a universe with just the right value of the cosmological constant could galaxies form, stars ignite, and life emerge. We live in such a universe not because it is the only possibility, but because it is the one where observers like us can exist. As you listen and drift into thought, imagine what it must have felt like for Einstein to confront his equations, to see them resist the idea of stasis, to push him toward a dynamic cosmos he was reluctant to accept. Picture him writing the cosmological constant into his notebooks, a small adjustment that carried such profound implications. Picture him years later, visiting the Mount Wilson Observatory, peering into the great telescope where Hubble had gathered his data, realizing that the universe itself was expanding. And then, imagine him reflecting on his so-called blunder, not knowing that one day, his constant would return as the cornerstone of a mystery greater than he had ever dreamed. The cosmological constant is a bridge between the human desire for stability and the universe's reality of change. It is a symbol of how science evolves, how ideas once discarded can re-emerge with new meaning. In Einstein's time, it was a way to preserve a static universe. In ours, it is a leading candidate for the force that accelerates expansion. What seemed like a mistake may have been a glimpse of the future, a whisper from the cosmos about its hidden energy. And so, as you rest beneath the quiet rhythm of this unfolding story, consider the strange journey of this constant. A mathematical invention to preserve balance, a blunder discarded in the face of expansion, a revival in the age of dark energy, and a puzzle that still resists solution. The cosmological constant is not just a number in an equation. It is a reminder that the universe often defies our expectations, that what we think of as errors may contain truth, and that even in the deepest mysteries, there may be echoes of insights left behind by those who dared to ask what holds the cosmos together in the quiet language of the cosmos. Two great mysteries dominate the story of what the universe is made of. They are called dark matter and dark energy. Though their names sound similar, their natures are profoundly different. Both are unseen, both are elusive, and both shape the universe in ways we can measure but not fully comprehend. If you imagine the cosmos as a grand symphony, dark matter is the unseen baseline, the hidden structure that gives galaxies their form, while dark energy is the accelerating rhythm, the invisible hand that pushes everything apart. Together, they define the universe for more than the matter we can see. And yet, despite their importance, they remain hidden from our senses, like shadows guiding the stars. To understand the difference between them, it helps to begin with ordinary matter, the kind we know best. Ordinary matter is what makes up everything we can touch, see, and interact with the atoms in your body, the iron in the Earth's core, the glowing hydrogen in the stars, and the interstellar gas floating between them. For centuries, scientists assumed that this visible matter was the entirety of the universe. But when astronomers began to look closely at how galaxies behaved, they discovered something astonishing. In the 1930s, Fritz Zwicky, studying galaxies in the Coma cluster, noticed that the galaxies moved far too quickly to be held together by the gravity of visible matter alone. According to Newtonian physics, the stars and galaxies should have flown apart long ago, if only visible matter were present. Later, in the 1970s, astronomer Vera Rubin confirmed this idea on a galactic scale. She observed the rotation curves of spiral galaxies and found that stars at the edges moved just as fast as stars near the center. If only visible matter were present, the outer stars should have orbited much more slowly. Something invisible was providing the extra gravitational pull needed to hold these galaxies together. That something became known as dark matter. Dark matter does not emit light. It does not absorb or reflect radiation. It is transparent, silent, and almost ghost-like. Yet it outweighs visible matter by a large margin. Roughly 27% of the universe is made of dark matter, while only about 5% is ordinary matter. Without dark matter, galaxies would not exist as we know them. They would not hold their shapes. Stars would not cluster into great cosmic islands. Dark matter acts as the scaffolding of the universe, the invisible framework upon which galaxies are built. Its gravity pulls matter together, allowing structures to form after the Big Bang. Dark energy, by contrast, works in the opposite direction. While dark matter pulls, dark energy pushes. Dark matter is attractive, binding galaxies together with unseen gravity. Dark energy is repulsive, driving galaxies apart and accelerating the expansion of space itself. Where dark matter acts on smaller scales, galaxies, clusters, filaments, dark energy acts on the largest scale of all, the entire cosmos. If dark matter sculpts the universe, dark energy paints its destiny. It can be helpful to imagine the universe as a vast cosmic tug-of-war. On one side, dark matter pulls inward, strengthening the gravitational bonds that hold galaxies and clusters together. On the other side, dark energy pushes outward, stretching the fabric of space itself, weakening those bonds on the largest scales. Ordinary matter, the stars and planets we see, contributes to the contest, but it is minor compared to these two giants. The strange truth is that everything familiar, every particle that makes up the world around us, is only a tiny fraction of reality. The vast majority of the cosmos is made of things we cannot see. About 27% is dark matter, and about 68% is dark energy. The rest, just 5%, is all the luminous matter, all the galaxies shining in the night sky, and all the atoms that form our bodies. This contrast between dark matter and dark energy can feel almost poetic. Dark matter, though invisible, behaves like matter in the sense that it clusters, gathers, and creates structure through its gravity. It is not evenly spread across the universe, but concentrated where galaxies form. Dark energy, on the other hand, does not clump. It appears to be spread smoothly and uniformly, permeating all of space like a subtle pressure. While dark matter binds, dark energy unbinds. While dark matter allows galaxies to exist, dark energy determines the fate of the cosmos itself. And yet, despite these differences, both remain unsolved mysteries. Scientists have yet to detect a dark matter particle directly. Many candidates have been proposed: WIMPs, axions, sterile neutrinos, but none have been confirmed. Experiments deep underground, shielded from cosmic rays, continue to search for rare interactions between dark matter and ordinary matter. At the same time, astronomers map the way galaxies cluster and bend light through gravitational lensing, hoping to infer dark matter's distribution. For dark energy, the mystery is even deeper. Unlike dark matter, it has no obvious particle candidates. Instead, it might be a property of space itself, a cosmological constant, or perhaps a dynamic field changing over time. It may even point to flaws in our understanding of gravity, what makes the puzzle even more intriguing is how the two mysteries interact. Dark matter shapes the cosmic web, the filaments of galaxies stretched across the universe. Dark energy stretches the space between these filaments, diluting them over time. The balance between the two determines what the universe looks like today and what it will look like billions of years from now. If dark matter had been too weak in the early universe, galaxies would never have formed. If dark energy had been too strong, the universe would have torn itself apart before stars could ignite. Somehow, the balance was just right, allowing structure to emerge, stars to shine, and life to evolve. As you drift into the thought of these cosmic forces, imagine standing at the edge of a galaxy, looking out across the void. Beneath your feet lies the gravitational embrace of dark matter, invisible but powerful, holding the galaxy together. In the distance, galaxies drift farther and farther away, carried by the push of dark energy, stretching space in every direction. You are caught between two forces, one pulling inward, one pushing outward, and you realize that this dance has shaped everything you see. Dark matter and dark energy are reminders that the universe is far larger, stranger, than our senses can grasp. They remind us that we live in a reality where the familiar is only the surface, and beneath that surface lies a hidden cosmos. When you look at the night sky, the stars twinkling overhead are just the tip of an iceberg, shining islands floating in an ocean of unseen matter and energy. The true universe is not just luminous points of light, but also the unseen forces that bind them and push them apart. In this way, the story of dark matter and dark energy is not only about science, but also about humility. It shows us how much remains unknown. It shows us that what we see is only a fraction of what is real. And it reminds us that the universe is not obliged to be simple or easily understood. It is vast, mysterious, and filled with forces that both create and destroy, bind and scatter, sculpt and erase. Between the pull of dark matter and the push of dark energy, we find ourselves in a universe that is dynamic, evolving, and ultimately beyond the full reach of our imagination. The universe is not a still painting, frozen in time, but a living story unfolding moment by moment. From the first spark of the Big Bang to the glittering galaxies we see scattered across the heavens, it is a cosmos in motion, constantly expanding and evolving. And if the past tells us that the universe had a beginning, then it is natural to ask what awaits in its future. This question, the fate of the universe, is deeply tied to the mystery of dark energy, the unseen force driving the expansion of space. Will the universe drift into eternal cold, rip itself apart, or find some delicate balance? The answers lie in how dark energy behaves, and how it competes with gravity across unimaginable scales of time. To understand these possibilities, imagine the universe as a balloon being inflated. In its earliest moments, matter and energy crowded together, dense and hot. Over time, the balloon stretched, galaxies drifted apart, and space itself expanded. Gravity, the force pulling matter inward, worked against this expansion, trying to slow it down. For most of cosmic history, gravity was winning, gradually decelerating the pace of expansion. But billions of years after the Big Bang, something shifted. Astronomers discovered that the universe was not slowing, but speeding up. Expansion was accelerating, driven by what we now call dark energy. And this acceleration leads us to ask, where does it all go from here? One scenario is known as the Big Freeze. In this vision, the universe continues to expand forever, driven by dark energy. Galaxies move farther apart, until one day, billions of years from now, the night sky of Earth, or whatever worlds exist then, will be empty of galaxies beyond our own. Light from distant galaxies will no longer reach us, stretched away by the accelerating expansion of space. Over time, stars will burn through their fuel and fade into darkness. Galaxies will grow dim, populated by cold remnants of stars, white dwarfs, neutron stars, black holes. On the longest timescales, even black holes will evaporate through a process known as Hawking radiation. leaving behind a universe filled only with thin whispers of radiation and stray particles. Space will expand faster and faster, thinning everything into near nothingness. The cosmos, once vibrant and full of light, will become a vast, cold expanse, an eternal winter without warmth. This is the Big Freeze, also called heat death, the quiet fading of the universe into darkness. Another possibility, far more dramatic, is called the Big Rip. In this scenario, dark energy is not constant but grows stronger over time. If the repulsive force of dark energy continues to increase, it could eventually overwhelm not only the gravity that binds galaxies together, but also the forces that hold stars, planets, and even atoms intact. In such a future, galaxies would first be torn apart, drifting into isolation. Then stars within galaxies would scatter, solar systems would unravel, and planets would drift free. As the expansion accelerated even further, the very atoms themselves would lose their bonds. Protons, neutrons, and electrons would be pulled apart as space stretched relentlessly. The entire universe would end in a catastrophic unraveling, an ultimate disintegration of matter itself. The Big Rip is terrifying to imagine, because it suggests not just the fading of the universe, but the destruction of all structure within it. Whether this happens depends on the exact nature of dark energy. If it is a cosmological constant, the Big Rip will not occur, but if it evolves over time with increasing strength, the universe may not escape this fate. Between the cold silence of the Big Freeze and the violent unraveling of the Big Rip lies another possibility: cosmic balance. Perhaps dark energy is not an unchanging property of space, nor a force that grows without end. Perhaps it changes in ways we do not yet understand. Some theories suggest that dark energy could decay or fade over time, weakening and allowing gravity to eventually slow the expansion. In such a scenario, the universe might expand for a time, then halt, and one day reverse into a contraction. This leads to the idea of the Big Crunch. In this picture, galaxies would stop receding and begin falling back together. The cosmos would collapse inward, growing hotter and denser, until all matter and energy are crushed into an unimaginably small point, perhaps a mirror of the Big Bang that began it all. The Big Crunch could even lead to cycles of expansion and collapse, an eternal rhythm of cosmic rebirth. Some call this the oscillating universe, a universe that never truly ends, but instead pulses endlessly through time, like a heartbeat across infinity. Yet the evidence we have today suggests that the Big Crunch is unlikely, at least under our current understanding of dark energy. Observations indicate that dark energy seems to be constant, not fading, and that the expansion of the universe will continue to accelerate. This points us more toward the Big Freeze or heat death scenario, though the true nature of dark energy remains unknown. Still, cosmologists cannot rule out surprises. If dark energy evolves, or if our understanding of gravity itself is incomplete, the story of the future could be very different. The fate of the universe is not just an abstract question of physics. It stirs something deep within us, because it touches on ideas of permanence and impermanence, beginnings and endings. Human lives are measured in decades, civilizations in millennia, planets in billions of years, but the fate of the cosmos stretches across unimaginable horizons of time. To think about the Big Freeze is to imagine a universe slowly losing its light, stars flickering out like candles in an endless night. To think about the Big Rip is to imagine a cosmos torn apart by its own expansion, undone by the very fabric of space. To think about the Big Crunch is to picture all of existence collapsing inward, only to perhaps explode outward again in an endless cycle. These visions are haunting, beautiful, and strangely comforting in their vastness. What makes these questions even more humbling is that they depend on something we cannot yet touch or see: dark energy. This unseen force, making up nearly 70% of the universe, will determine whether everything fades into silence, shatters in violence, or cycles in endless rebirth. Every telescope aimed at the sky, a survey of galaxies, every measurement of cosmic expansion is, in some sense, an attempt to peer into the future as much as into the past. For now, the stars continue to shine. Galaxies still spin, their shapes held together by dark matter, while the space between them stretches, drawn by dark energy. We live in a fleeting moment of cosmic time, when the night sky is still rich with galaxies and stars. Billions of years from now, that sky will look very different, perhaps empty, perhaps chaotic, perhaps collapsing inward. But tonight, as you let your thoughts drift across the expanse of space, you are connected to that vast story, caught in a universe whose future is still unwritten, suspended between gravity's pull and dark energy's push, a delicate balance that will one day decide the ultimate fate of everything you see when you look up at the night sky. When we speak about dark energy, we speak of something mysterious, unseen, and yet overwhelmingly powerful. It fills the universe, shaping its future, and yet we cannot bottle it, touch it, or even detect it directly. For scientists, this is both frustrating and exciting. Frustrating, because such an enormous part of reality remains hidden from our instruments. Exciting, because every new experiment is like turning a key in a locked door, revealing hints of what might be waiting on the other side. In the quiet laboratories of Earth, and through telescopes orbiting high above our atmosphere, humanity is slowly piecing together the puzzle of dark energy, seeking to understand what it is, how it works, and what it means for the fate of the cosmos. These ongoing experiments and observations form one of the most ambitious projects in the history of science, a quest to measure not only the present but also the past and future of the universe itself. The story begins with light, because in astronomy, light is our messenger. When astronomers discovered the acceleration of the universe in the 1990s, they did so by studying the glow of exploding stars, supernova, in galaxies billions of light years away. Those faint flickers carried news from a time when the universe was much younger, and by comparing how bright they appeared to how bright they should have been, scientists realized the expansion of the universe was speeding up. This discovery lit the spark for an entire generation of new instruments and projects, designed to measure cosmic expansion with more precision than ever before. One of the central tools in this quest is the study of the cosmic microwave background radiation, the afterglow of the Big Bang. This faint radiation bathes the entire universe, a whisper from nearly 14 billion years ago, when the cosmos was only a few 100,000 years old. Satellites like the Wilkinson Microwave Anisotropy Probe, or WMAP, and later the European Space Agency's Planck satellite have mapped this radiation in exquisite detail. The tiny variations in its temperature across the sky reveal not only the early conditions of the universe, but also the influence of dark energy on its evolution. These maps have become cosmic fingerprints, showing us the proportions of ordinary matter, and dark energy. What they tell us is astonishing. Nearly 70% of the universe is made up of this mysterious dark energy, with only a small fraction being the matter we see in stars and planets. But the story does not stop there. To study dark energy, scientists need to map the structure of the universe on vast scales, tracing how galaxies are arranged across billions of light years. Imagine looking at the night sky not as scattered pinpoints of light, but as part of an enormous cosmic web. Filaments of galaxies stretched across space like strands of a spider's web. The patterns of this web hold clues about how the universe has expanded over time. Projects like the Sloan Digital Sky Survey, with its massive catalog of galaxies, have revealed this structure in remarkable detail. By measuring something called baryon acoustic oscillations, subtle ripples imprinted on the distribution of galaxies by sound waves in the early universe, astronomers can track how cosmic expansion has unfolded, giving them another way to measure the influence of dark energy. As technology advances, even more ambitious surveys are being launched. The Dark Energy Survey, based in Chile, has used a powerful telescope to observe hundreds of millions of galaxies, measuring their shapes, positions, and brightness. These measurements allow scientists to trace how galaxies cluster under the pull of gravity, and how dark energy pushes them apart. Meanwhile, Other observatories such as the Subaru Telescope in Hawaii and the upcoming Vera C. Rubin Observatory are preparing to take this mapping to entirely new levels, imaging the sky with breathtaking depth and scale. The Rubin Observatory, once it begins its legacy survey of space and time, will collect a vast treasure of data, imaging the entire southern sky every few nights, creating a time lapse of the universe itself. From this river of information, astronomers hope to tease out the subtle fingerprints of dark energy, hidden in the motions of galaxies and the bending of light across cosmic distances. Space-based missions add another layer to this search. The European Space Agency is preparing a spacecraft called Euclid, designed to study dark energy and dark matter by observing billions of galaxies up to 10 billion light-years away. Euclid will map how galaxies are distributed and how their light is distorted by gravitational lensing, the bending of light by matter. This effect is like a cosmic magnifying glass, allowing scientists to measure the growth of structure in the universe, which is directly influenced by dark energy. Across the Atlantic, NASA is working on the Nancy Grace Roman Space Telescope, a mission dedicated to studying dark energy using multiple methods, including supernova observations and weak gravitational lensing. Together, Euclid and Roman will create a new era of precision cosmology, providing a detailed picture of the cosmos on scales never before achieved. Meanwhile, theorists are working alongside observers, building models of dark energy and testing them against data. Some theories suggest that dark energy is simply the cosmological constant, Einstein's idea of a constant energy density filling space. Others imagine it as a dynamic field, sometimes called quintessence, that changes over time. Still others wonder whether dark energy might be an illusion, a sign that our understanding of gravity itself is incomplete on cosmic scales. Modified theories of gravity, such as those extending Einstein's general relativity, are being explored to see if they can explain the acceleration without invoking an unknown form of energy. Every new dataset provides another chance to test these ideas, to confirm or refute them, and to bring us closer to the truth. These experiments and observations are not only about numbers and equations. They are about perspective. Every galaxy mapped, every photon detected, is a message from across the depths of space and time. When we study the light from a distant supernova, we are not just seeing a star explode, we are watching the universe reveal its hidden laws. When we chart the distribution of galaxies, we are drawing a portrait of the cosmos itself, one that stretches across billions of years. The search for dark energy is also a search for our place in this grand story, because in understanding what drives the expansion of the universe, we understand more about the stage on which all of existence unfolds. In the United States, this pursuit is not just a scientific ambition, but a national collaboration, with institutions across the country contributing telescopes, satellites, and supercomputers to unravel the mystery. From observatories in the deserts of the American Southwest to control rooms at NASA, teams of scientists, engineers, and students are devoting their efforts to exploring dark energy. And yet, despite the vast complexity of the instruments, the essence of the quest remains profoundly simple: to ask what the universe is made of, and what will become of it. Ongoing experiments and observations remind us that science is not static. It is a journey, unfolding step by step, generation by generation. Just as Galileo once turned his telescope toward the skies and revealed moons around Jupiter, today, we turn ever more powerful instruments toward the cosmos, hoping to reveal the invisible energy that shapes it. In the coming decades, new discoveries will continue to emerge, each one sharpening the picture, each one bringing us closer to understanding the force that drives the universe's expansion, each one inviting us to listen to the quiet story written in starlight across the endless night sky. When we speak of dark energy, we are speaking of something that challenges not only the boundaries of physics, but also the edges of human imagination. It is a force that seems to come from nowhere, invisible, and intangible, yet it accounts for nearly 70% of everything that exists. We do not see it in the stars above us or in the glow of galaxies. We do not feel it in our bodies, or measure it in the everyday world around us, and yet, without it, the universe would not be what it is. Dark energy is a mystery of science, but it is also a mirror for philosophy, a question that invites us to look not only outward, toward the cosmos, but inward, toward our own understanding of reality and meaning. Throughout history, humanity has looked up at the night sky and asked questions that were not only scientific, but deeply human. What is out there? Why are we here? How does the universe work? And what is our place in it? Ancient civilizations traced patterns in the stars, telling stories of gods and heroes, weaving myths to explain the movements of the heavens. Over centuries, science grew from these stories, replacing myth with mathematics, observation, and theory. But even as our explanations became more precise, the sense of wonder remained. Dark energy is one of those discoveries that renews the sense of wonder, reminding us that no matter how much we know, the universe still holds secrets that defy comprehension. Philosophers might say that dark energy is a symbol of the unknown, a reminder that the universe is not a closed book, but an open story, with pages yet to be written. It humbles us, because it shows how small our knowledge still is, despite centuries of progress. When scientists look at the cosmos and conclude that most of it is invisible and unexplained, they are, in a sense, echoing the same humility that philosophers have expressed for millennia. The idea that human knowledge is always partial, always incomplete. This humility is not a weakness but a strength, because it drives us to keep searching, to keep questioning, to keep reaching toward truths that lie just beyond the horizon. For ordinary people, not just scientists, dark energy can also be a metaphor. It can stand for all the unseen forces in life that shape our paths, the influences we cannot measure or fully explain. Just as galaxies drift apart under the push of dark energy, our lives are often carried forward by invisible currents, chance meetings, unexpected opportunities, quiet inspirations that guide us toward the future. We do not always understand these forces, but they are there, shaping the expansion of our own personal universe. In this way, the mystery of dark energy resonates with the mystery of human experience itself. There is also something profoundly beautiful in the idea that the universe is not static but dynamic, always changing, always expanding. For much of history, people imagined the cosmos as eternal and unchanging, a perfect order that existed outside of time. But now, we know that the universe has a history, a beginning, and perhaps even an end. Dark energy is part of that story, a force that writes the future of the cosmos, determining whether galaxies will drift forever into the darkness or be torn apart in some unimaginable finale. To reflect on this is to reflect on time itself, on the fact that everything, even the stars, even the galaxies, exists within a flow of change. For us as human beings, this truth can be both unsettling and comforting. Unsettling, because it reminds us of impermanence. Comforting, because it shows that change and motion are not flaws, but the essence of existence. When we think of dark energy philosophically, we might also think of it as a lesson in perspective. We live our lives on a small planet circling an ordinary star in one galaxy among billions. From our point of view, the cosmos is vast beyond comprehension, and dark energy operates on scales far beyond our senses. But to the universe itself, dark energy is simply part of its nature, as ordinary as gravity or light. This shift in perspective invites us to step outside of our human-centered view of reality and consider the universe on its own terms. It reminds us that our stories, our struggles, our triumphs, while deeply meaningful to us, are set against a backdrop that is infinitely larger. For some, this perspective might feel diminishing, but for others, it can be liberating, an invitation to see ourselves as part of a grand, interconnected whole. There is also a poetic dimension to dark energy. Imagine galaxies like tiny lanterns, glowing in the night, carried apart by an unseen wind. Imagine space itself stretching, like a fabric being pulled at its edges, the galaxies embedded in it, like jewels. This image is both scientific and poetic, blending numbers and metaphors, equations and imagery. Science often deals in precision, in measurements and predictions, but philosophy reminds us that the meaning of these discoveries lies not only in their technical details, but also in how they shape our imagination, how they change the way we see the world. In this sense, dark energy is more than a term in a physics textbook. It is a story, one that invites us to marvel at the unknown, to embrace the mystery, and to dream of what lies beyond. There are also ethical and existential reflections that arise from the mystery of dark energy. If most of the universe is invisible and unexplained, what does that say about our search for certainty in life? Perhaps it suggests that uncertainty is not something to fear, but something to accept. Just as scientists continue to explore without knowing all the answers, we too can live our lives with curiosity and courage, even when the path is unclear. Dark energy teaches us that not knowing is not the end of the journey, but the beginning. It invites us to dwell in the mystery, to find peace in the questions, and to trust that even the unknown can have meaning. For the United States, and for the world, the study of dark energy is not just a scientific project, but a human one. It is a collaboration across cultures, disciplines, and generations, uniting people in the shared pursuit of knowledge. It reminds us that science is not just about solving equations or building instruments. It is about expanding the human spirit, about reaching into the darkness with the light of curiosity and imagination. In a divided world, this pursuit can serve as a reminder that some questions belong to all of us, that the cosmos itself is a shared inheritance, and that its mysteries are an invitation to unity. As we reflect on dark energy, we find ourselves standing at the boundary between what is known and what is unknown. We stand on the edge of a vast ocean, with only a few drops in our hands, gazing out at the endless waves. Some may find this overwhelming, but others find it inspiring. For in those waves lies the promise of discovery, the possibility of wonder, and the reminder that the universe is always larger, always stranger, always more magnificent than we imagine. And in that reminder lies a gentle truth, that to be human is to question, to seek, and to dream, even in the face of the great unknown that stretches beyond the stars. As we come to the end of our quiet journey through the mysteries of dark energy, we can look back at the path we have traveled together. We began with the discovery that the universe itself is not still, but expanding, a revelation that changed how we see the cosmos and ourselves. The work of Einstein, Hubble, and countless others opened the first door, showing us that space is alive with motion, a fabric stretching silently across time. From there, we stepped into the enigma of dark energy itself, a force unseen and unknown, yet powerful enough to govern the destiny of galaxies. It became clear that even though we cannot touch it, measure it directly, or capture it in our instruments, its presence shapes the grand structure of everything we know. We reflected on the evidence, the distant supernova shining like cosmic markers across billions of years, the patterns written in the faint glow of the cosmic microwave background, and the surveys that map the silent scaffolding of galaxies. These signs are whispers from the universe, clues that lead us to the invisible hand guiding expansion. We trace this mystery back to Einstein's cosmological constant, once dismissed as a mistake, and now reborn as a possible key to understanding why space itself accelerates outward. In this way, history and science intertwined, reminding us that knowledge is never final, that even what seems like an error can one day become a revelation. Along the way, we separated dark energy from its companion mystery, dark matter. Though they share a name, their roles are vastly different. Dark matter binds galaxies together with unseen gravity, while dark energy pushes them apart with unseen pressure. Together, they form the hidden backbone of reality, a framework on which stars and planets and life itself are written. Their presence deepens the mystery, showing that most of the universe is not what we see, but what we cannot This led us to contemplate the fate of everything. Will the cosmos drift into a cold and silent eternity, with galaxies too far apart to see one another? Will it one day tear itself apart in a great rip of unimaginable violence? Or will there be some balance, some slowing of this expansion that keeps the cosmos alive in ways we have not yet imagined? These questions are not only scientific, but profoundly human, for they remind us that even the universe itself has a future, and that we, as a small part of it, are bound within that future too. We considered the experiments and observatories working tirelessly to unravel this enigma: telescopes on mountain tops, satellites circling Earth, instruments that peer into the farthest reaches of time and space. These projects are more than machines. They are the eyes of humanity, extended into the night, searching for the faintest traces of truth. Through them, we continue to ask, to wonder, to seek, even when the answers remain hidden. Finally, we reflected on the philosophical weight of dark energy, on what it means to live in a universe where most of what exists is invisible and unknown. This knowledge humbles us, but it also inspires us, for it teaches us that mystery is not an obstacle, but an invitation. It reminds us that uncertainty is natural, that not knowing is a space for growth, and that discovery is as endless as the cosmos itself. Dark energy is more than a term in physics. It is a symbol of the vastness of existence, and the small yet beautiful part we play in it. In the end, to speak of dark energy is to speak of wonder. It is to stand beneath the stars, to feel the immensity of space above, and to recognize that we are part of a story larger than ourselves. The universe is not finished. It is expanding, knitting new chapters with every passing moment. And though we do not yet know where that story leads, we can rest in the knowledge that to be human is to ask the question, to seek the answer, and to marvel at the mystery that carries us forward, just as it carries the galaxies endlessly into the night sky.